Good day, students. My name is Siri, and I'll be taking you physics. And today's we're going to be looking at waves. So get your writing materials, your calculators, and I'll be right back. Welcome back. Moving on straight to the topic, we have wave. So what is wave? Wave is a disturbance that transfers energy through a medium, and they are fundamental concept in physics. What does this mean? This simply means that wave involves the transfer of energy, and it must involve a medium. And this transfer of energy does not involve the actual displacement of the medium, meaning that the medium does not have to move for wave to have occurred. And wave can be classified into different types. We have different types of wave, and their understanding and properties of these waves determine what the type of wave will be. So we have different types of wave. We have what is called the mechanical wave, and we have the electromagnetic wave. For the mechanical wave, this is a type of wave that requires a physical medium for it to be propagated. An example is your water wave and the sound wave. So looking at these types of wave, for the first one, which is the mechanical wave, you realize that for your mechanical wave, which is your sound wave and your water wave, for example, you discover that anytime you want to cause ripples in a pool of water, you have to drop something into the pool for the wave to have occurred. Looking at if this is a pool of water and I drop a pebble into this pool, you discover that there will be circles around that pebble. These circles are what we call waves. So you also find it in sound wave. For a sound to be made, like actually I hear my voice, is as a result of I, which is the medium. If I close my mouth and I'm not speaking, there will be no sound coming from my mouth. Therefore, no wave will be produced. So looking at the second one, which is the electromagnetic wave, this is a type of wave that does not require a material medium for it to be propagated. Meaning that you do not have to hit the object for the light to come out, or you do not have to drop a pebble, as in the case of water wave, for the wave to be what propagated. So an example of your electromagnetic wave is your light wave and your radio waves, like how you get your radio signals or your network signals. They are electromagnetic. They travel through space, so they travel in a vacuum for you to get the wave, and does not require a material medium. So we're going to be talking about the properties of wave. What are the properties of wave? Before we talk about the properties of wave, I'm going to draw the diagram of a progressive wave. So this is a progressive wave. So this is a progressive wave moving from this point and continue that movement, as you can see in the direction. So in a progressive wave, there are certain properties that a wave must exhibit, and one of them is the amplitude of the wave. The amplitude of a wave is the maximum displacement of a wave from the equilibrium position. What do we mean by the equilibrium position? This point here, where this wave is starting its motion, is the equilibrium position. This is the point of zero. So from this point down to the highest point that the wave will get to is what we call the amplitude. So from here down to this point is the amplitude of the wave. That's the amplitude of the wave, and it is measured in meters because it's talking about what? Displacement. Then we have the wavelength of the wave. The wavelength of the wave is the distance between two successive crests or trough. Two successive crests or trough. What do we mean? This point here, the highest point of a wave, is called the crest. This point here is called crest, while this point here is called the trough. So the distance between two successive, between this crest and this crest, is what we call the wavelength. This is the wavelength of the wave. And we use what? Lambda to represent it. So this is lambda, and it is used to represent the wavelength of a wave. It is measured in meters because it's talking about what? Distance. Also, your wavelength can also be the distance between two successive trough. So from here down to this place is also wavelength. So it's either the crest, distance between two successive crests, or the distance between two successive trough is called the what? Wavelength of a wave, and it is measured in meters. The next property of a wave is the frequency of a wave. The frequency of a wave is the number of oscillation or cycle per second. The number of oscillation or cycle per second. What does this mean? It means that the frequency of a wave, frequency, is number of oscillations or number of cycles over time. So the number of cycles that a wave is able to complete per time is called the frequency of a wave, meaning that how fast can this wave carry out certain parameters? How fast can this wave bring out circles? How fast can it complete a crest and a trough? So from this point, here is from this point of 0 down to this point is one complete oscillation or one complete circle, because this is half a circle and this is half a circle. So when you add it, it completes what? A circle. So the time from here down to this point is called the number of circles is able to complete between a particular period of time is called the frequency of a wave, and it is measured in hertz. Hertz. Hertz can also be per seconds. You can also call it as per seconds. It is measured in hertz, which is also per seconds. Okay, the next parameter that we're going to be looking at, or the next property of wave that we'll be looking at, is the speed of a wave. The speed of a wave. The speed of a wave is the rate at which a wave propagates through a medium. The rate at which a wave propagates through a medium. I already know what speed is. It's the same thing that we have for the motion of a body. The same thing for wave also. So the speed of a wave, wave speed, is the product of the frequency and the wavelength. The product of the frequency and the wavelength, which is what? F lambda. So whenever you multiply the frequency of a wave and the wavelength of a wave, you are going to get the speed of the wave, and it is measured in meter per second, because anything speed is always measured in meter per second. Then we have the period of a wave. The period of a wave. This is the time it takes a wave to complete one cycle or one oscillation. The time it takes a wave to complete one cycle or one oscillation is called the period of a wave. And the period of a wave, period, is time taken over the number of cycles. This can also be that my period is time over number of cycles. And because our period is talking about time over number of cycles, it is measured in seconds, just as period for your simple harmonic motion. So it is measured in seconds. So that takes us to the behavior of a wave. What are the certain things that what we determine how a wave behaves? So from how a wave behaves, you can tell that it has certain things that can be seen in the wave to say, okay, this is what the wave is doing at this particular time. This is what the wave is doing at this particular time. So we have different behavior of the wave. The first behavior of the wave is the reflection. What is reflection? This is the change in the direction of a wave when it hits a surface and bounces back. So whenever a wave hits a surface and bounces back, there is what we call reflection. So what do I mean? Let's say this is a plane mirror. If this is a plane mirror, and light is incidented on this plane mirror. The light will be reflected from the mirror. So what do I mean? If you point your torchlight at a plane mirror, the gravity with which the light hits the mirror is the same way that the light is going to be what? Reflected from the mirror. So you are going to see the light on the wall if that mirror is on the other wall. Why? Because the light has been what? Reflected from the mirror. Same way as all types of waves. So whenever a wave hits an obstacle, it will redirect and bounces back, and that becomes what? Reflection of a wave. So what I want to call what? Refraction of a wave. What is refraction of a wave? This is the bending of a wave when it passes from one medium to another. So when a wave passes from one medium to another, it bends. For example, if you put a cup of water in a, if you put water in a glass cup and then you put spoon inside, when you look through the glass, you discover that what is as though the spoon is bent. And that is because what? The spoon has transferred itself from air to water. So looking at it through the glass, you discover that what? I'm looking at it through a different medium and it's inside a different medium. The glass is a medium, the water is also what? A medium. So because it is inside the water and I'm looking at it through the glass, which is a different medium, you are going to discover that what? There will be what? The redirection of that spoon. The same way as what? All types of wave. So when a wave transfers from one medium to another, there's usually what? Redirection of that wave. And that phenomenon is called what? Refraction of a wave. The next behavior of wave is the diffraction of wave. What is diffraction of wave? This is the bending of a wave when it hits an obstacle. So when a wave hits an obstacle, it bends around the obstacle. For example, if I have light wave traveling in this direction, this is a beam of light traveling in this direction, and I have an obstacle, let's say a block here. So if there is a small opening in the block, as in this case, immediately this wave hits this obstacle, which is the block, is going to bend and pass through this small aperture. The small opening here is called an aperture. So it's going to bend around this aperture and form wave in this format. Why? Because the wave at this point has diffracted. It has what? Passed through the small opening and what? Is now bending around this obstacle. This phenomenon or behavior of a wave is called the diffraction of a wave. The next behavior of a wave is the interference of a wave. What is the interference of a wave? This is the combination of two or more waves resulting in the formation of a new wave pattern. What do we mean by this? Let's say a wave is in this format, it's traveling in this direction. Let's say this is a wave traveling in this direction. Interference is another wave either traveling in this same direction or a wave traveling in the opposite direction, as in this case. So these two diagrams here or graphs are showing interference of a wave. This is what we call constructive interference, and this is what we call destructive interference. Why? This wave is traveling in the same direction as the earlier wave, but in the destructive interference, the new wave is traveling in opposite direction of the previous wave, and this is what we call interference of a wave, because a new wave pattern has been formed in both cases. We call it what? Interference of a wave. So what are the applications of wave? The first application of wave is in sound, is sound wave. You apply waves in music. You use it in communication and use it in medical imagery. And you are, what kind of wave are you applying there is what? Sound wave. We also apply waves in vision, like that's that type of wave is called what? Light wave. We apply it in vision, we apply it in optical communications, and we also apply it in medical imaging. Like when you go for your ultrasound, and the others, what they are doing is the what application of wave. We also apply it in wireless communication, like how you are able to talk to somebody that is in a different country, in a different state, is what through waves, which is what radio waves. So you're able to what communicate with them or listen to your television and radio stations or through what wave. And we apply it in what broadcasting and also in navigation. Like if you want to know the location of a particular place while you are moving towards that place, what you are doing is what application of wave. So that takes us to our wave equations and formulas. So like we already established before, we said that what the formula for the speed of a wave is v is equal to what f lambda, which we wrote earlier. We said that what v is equal to what f lambda. This is the formula for the speed of a wave. So that takes us to wave equations and formula. So the wave formulas that we have the formula for the speed of a wave, the formula for the frequency of a wave, and the formula for the period of a wave. And we established earlier that the velocity or the speed of a wave is f lambda, which is the product of the frequency and the wave length. So our f here represents frequency, and our lambda here is representing wavelength. So we also have the formula for the period of a wave. The formula for the period of a wave, we say that the period of a wave is time over the number of circles. Time over the number of circles. And this can also be the same thing as saying that the period of a wave is 1 over the frequency of a wave. Why? Because we said earlier that the frequency of a wave is number of circles over time. So automatically, this simply means that the period of a wave is the reciprocal of the frequency of a wave and vice versa. That is to say that the frequency of a wave is also the what reciprocal of the period of a wave. So we're going to look at some practice questions to be able to solve questions on this topic. The first question here says a wave has a frequency of 50 Hz. So we have the frequency of the wave as 50 Hz and a wavelength of 2 meters. So we have the wavelength as 2 meters. And then they say calculate the speed, calculate its speed. So its speed we do not know. And we already know that the velocity of a wave or the speed of a wave is f lambda. So automatically this means that the speed of this wave is 50 times 2, and that will give me 100 meters per second. So the question number 2 says that a wave has a speed of 300 meters per second. So the velocity has been given as 300 meters per second. And they said with a wavelength of, so the wavelength has been given as 1.5 meters. They say calculate its frequency. So the frequency here is unknown. And we know that the velocity is equal to f lambda. This means that the frequency is velocity over lambda. So with this, we know that the frequency of this wave is going to give me 300 divided by 1.5, which is the same thing as saying 300 divided by 15 over 10, or you can say 300 times 10 over 15. 15 here, 1, 15 here will give me 20. So, and that will give me 200 Hz. Okay, we're going to be looking at types of waves based on direction of travel and movement of material. The earlier type of wave that we talked about was based on whether a material medium is needed or not. So, but this type of wave, we're talking about what? The direction of travel of the wave and the movement of the material. Under this type of wave, we have what we call the transverse wave and the longitudinal wave. Transverse wave and longitudinal wave. So, the transverse wave, which is the first one, in the transverse wave, the particles of medium oscillate perpendicular to the direction of the wave. The particles of the medium oscillate perpendicular to the direction of propagation of the wave. What does this mean? If I have a wave traveling in this direction, let's say I have a wave traveling in this direction. Let's say this is a spring, for example, and then the wave is moving in this direction. Then the particles of the wave will be vibrating in the opposite direction. So the wave is moving horizontally, and the particles that are responsible for this wave are moving in opposite direction. They are moving what? Vertically. This type of wave is called transverse wave. While for the longitudinal wave, the wave particles and the wave motion are moving in the same direction. When the wave particles and the wave motion are moving in the same direction, we call it what? Longitudinal wave. Example is your sound wave. So if you have seen the speakers, when you look at this, your loudspeakers are what? The particles of the speaker are moving in and out that way, the same direction as the sound is coming out. So that sound is also moving in that same direction as the particles of that speaker. That type of wave is called what? A longitudinal wave. So that takes us to the characteristic of wave motion. What are the characteristics of wave motion? The first characteristic of wave motion is energy transfer. Energy transfer. Wave transfers energy from one point to another without transferring the matter. So I explained that when I was talking about the definition of wave, when I told you that what wave is what? A disturbance that transfers energy from one point to another without the actual displacement of the medium. So the medium is not what moved from its position, but the what? Energy is transferred from one point to another within the wave motion. Then we also have what is called wave intensity. The intensity of a wave is the power per unit area carried by the wave. The power per unit area carried by the wave is called the intensity of the wave. That could also mean the strength of the wave. So the next thing is what? Applications of wave properties. How do we apply the properties of a wave? We apply the properties of a wave in medical imaging. So when during your ultrasound and your MRIs, when you go for your MRIs to check your brain and how it functions, or you go for your ultrasound to check how the baby in your womb is performing, what you are doing is what? Medical imagery. And what they use in getting those pictures is what? Wave. They also apply wave in communication. Like I said earlier, for you to be able to hear someone who is in a different country, in a different state, via a telephone conversation, is the use of what? Wave. And we also apply it in transferring information during broadcasting in your televisions and your radio station. So that takes us to your wave interference and superposition. Your wave interference and superposition. So the principle of superposition works this way. When two or more waves overlap in a medium, the resultant displacement at any point is this vector sum of the displacement of the individual wave. What does this mean? When two or more waves are allowed to overlap within a medium, for you to get the total sum of the displacement, you add all the displacement of the individual wave. Each wave has its own displacement. So when you add all the displacement of individual waves together, what you are going to be having is the vector sum, and that is what the principle of superposition of a wave. So that takes us to the types of interference. I drew a diagram on the board earlier that is explaining the types of interference of a wave. When we talked about the constructive and the destructive interference, where I drew a diagram like this and said that this is a constructive interference. This is a constructive interference, as in this case. So when the waves are moving in the same direction, two different waves are moving in the same direction, it is called constructive interference. And when they are moving in opposite direction, it is called destructive interference. destructive interference. So your destructive interference leads to the formation of what we call a standing or stationary wave. So what are the applications of interference? What do we use interference for? How do we apply this principle of interference? One of the ways we apply interference is in noise cancellation. Noise cancellation. In your telephones and other devices, your interference is used to reduce unwanted sound. In some of your AirPods now, when you are talking, you discover that although there are other sounds there, your AirPod does not pick those sounds. Instead, you only hear the voice of the person that is speaking to you directly. And the reason is that AirPod has a noise cancellation principle that is working with interference of a wave, so that any wave that is not directly picked by the earpiece of that particular earpod is not transmitted, because it is interfering with the original wave, and that is noise cancellation. So your interference is also applied in interferometry, and this is the use of interference in astronomy to determine small distances using the wavelength. So when you use the wavelength to determine small distances between planetary bodies, what we are doing is interferometry. That takes us to wave diffraction. Wave diffraction. And we explained earlier that the diffraction of a wave is simply the bending of a wave around obstacles or through small openings, where I drew a diagram. So if I have light wave traveling in this direction, let's say light wave is traveling in this direction, and I have an obstacle with a larger opening compared to the one I drew earlier. With a larger opening, the wave particles that will be formed will be in this format. Why? Because the aperture is larger compared to when the aperture is smaller. So when the aperture is smaller, it forms semicircular wave formed as a result of the opening. And this principle is called the diffraction of wave. And you can see it in water waves. Water waves diffract around rocks or through narrow channels. So if I have water passing through, let's say this is a stream, and water is moving in this direction. Let's say this is a stream. This is a stream, and water is moving in this direction. And at one point, discover that there's a big rock here, and there's a small hole. There's another big rock, and there's a small hole. You discover that all the water that are passing through that stream will pass through that small opening that is between the two rocks. This is what we call diffraction of a wave. We also have diffraction present in sound wave. That is why you can hear the sound from bodies that you are not directly facing. If you are walking in your street, you can hear the sound of music, even though the music is not directly opposite you and you cannot see it. So that is the diffraction of sound. So that takes us to the applications of diffraction. And one of the applications of diffraction is in acoustics. In acoustics, we use diffraction in designing auditoriums and other spaces where sound quality is critical. So if you have been to certain auditorium, discover that while you are inside the auditorium, the sound is very loud, but outside the auditorium, you can barely hear the sound. Why? Because they use the principle of diffraction in building those auditoriums. Another application of diffraction is in optics, and we use it in diffraction gratings in optics to apply diffraction in diffraction gratings. So that takes us to standing waves. What are standing waves? A standing wave is a wave that oscillates in place with node and antinode that do not move. And I explained earlier that whenever we have a destructive interference, what you have is a standing wave. Why? You will not notice the node and the antinode of this particular wave moving. They remain in stationary position. So that's what we call a standing wave. when the wave oscillates in place, when it's oscillating in one position, not what? Moving the antinode and the node. An example is your guitar string. When a guitarist is playing his guitar string, you discover that what, while you are staring at the strings, it's as though the strings are not moving when it's playing or when it plugs the strings. Why? Because that particular string is in standing waves. You also observe standing waves in organ pipes. Standing waves are observed in organ pipes when organ pipes are played. So we also have applications of standing wave. How do we apply standing wave? We apply standing wave first in music, like in the case of the guitar and the organ pipe. We apply what? Standing waves in what? Producing sounds from musical instruments. We also apply standing waves in engineering for designing structures that can withstand vibrations. So they pose certain amount of vibrations to different structures and help to design those structures so that they can withstand certain vibrations, even from minor earthquakes. That takes us to how wave is present in our everyday life. So wave science in our everyday life. So first, we have wave science first in weather forecasting. We use wave science to be able to what? Determine the weather, the temperature, the patterns of hurricanes and storms of the weather condition for that day. We also use wave science in oceanography. We use to determine the current tides and waves of water bodies in oceanography. We also use it in medical applications, like we have explained earlier, that we use it in ultrasound and MRIs. We also use it in communication, like in your radio, telephones, and the internet as a whole in communication. So we also use it in different disciplines, like in physics. We use your applications of wave in physics. We also use your understanding of wave in engineering. Okay, so that takes us to interdisciplinary connections. So in interdisciplinary connections, we have one of the disciplines here is in physics. So wave science is a fundamental aspect of physics, and understanding waves is essential for understanding various physical phenomena. So in the discipline of physics, we apply waves in certain principles or phenomena in physics, and we use waves in explaining them. We also use waves in engineering. That includes your mechanical engineering, your civil engineering, and etc. So that takes us to a subtopic called light wave. So what are light waves? Light waves are a form of electromagnetic radiation that is visible to the human eye. So it's a form of electromagnetic radiation visible to the human eye. We explained earlier from the beginning that what? One of the examples of your electromagnetic wave is your light wave. And as this room is, it is lighted up. Why? So that what? The pictures and images in this room can be visible to the human eye. Hence, this room is what? Lighted up. The light here makes it possible for us to be able to see. So they are a crucial aspect of our daily lives, enabling us to see and perceive the world around us. So light wave what enables us to see things that are happening around us on a daily basis. What are the properties of light wave? The properties of light wave are similar to the properties of wave generally, and one of them is the wavelength. So light generally have what? Wavelength. So the distance between two consecutive peaks or trough, crest or trough of the wave is what we call the wavelength. And the wavelength of light ranges from about 300 to about 700 nanometers, depending on the medium in which the light is present. We also have the frequency of light wave. the frequency of light wave is inversely proportional to the wavelength. The frequency of light wave is inversely proportional to the wavelength. What does that mean? This means that the frequency of light wave is 1 over the wavelength. So that takes us to the speeds of light wave. Light wave travels at approximately 299,792,454 meters, which is approximately about 300 million meters per second in a vacuum. So in air, wave travels at about 300 million meters per seconds in a vacuum. So that takes us to the next property, which is amplitude. And the amplitude of a wave, like we explained before, is the distance between the equilibrium position of the wave and the maximum point on the wave, which is the crest. So that takes up the types of light wave. What are the types of light wave? The first type of light wave that you have is the visible light. The visible light. This is the portion of the electromagnetic spectrum that is visible to the human eye. So light wave, we have the one that can be visible to the human eye and the part that cannot be visible to the human eye. So the one that we can see is what we call the visible light. And it is a part of the electromagnetic spectrum that we're still going to be talking about. So that part is what we call the ultraviolet light. The ultraviolet light has a shorter wavelength than the visible light, and it is not visible to the human eye. So when we say ultraviolet rays from the sun, which is what the ozone layer is supposed to block the human body from, the ultraviolet rays of the sun can cause cancerous cells to develop, and that ultraviolet rays are not visible to the human eyes. We cannot see it with our normal eye. So what we are seeing from the sun is what we call the visible light, and the ultraviolet rays are not visible. We also have the infrared light. The infrared light are also not visible to the human eye, and they have a longer wavelength than the visible light, and they are not visible to the human eyes. Before now, back then, at the invention of phones, we were using infrared light or infrared rays to transfer data from one phone to another. And you can also find your infrared light in your remotes that I would use to transfer whatever information you are pressing on your remote down to your televisions and all other electrical appliances. That takes us to the behavior of light wave. Just as we have behavior of wave generally, these same behaviors are also applicable to light wave. And one of them is reflection. So light waves can be reflected, light wave can be refracted, light wave can be diffracted, and light wave can be interfered with. And they all have similar properties as we have talked about when we're talking about the properties of wave generally. So what are the applications of light wave? Applications of light wave. One of the applications of light wave is in vision. Without light, it will be impossible for us to see. So light made it possible for us to see. If light were to be removed from the world would be a dark place. So light made it possible for us to see. So it's applicable in vision. Another application of light wave is in optical communication. So light waves are used in fiber optics. So currently fiber optics is one of the ways we transfer data, and in advanced countries they even use it for dissemination of information as well as our internet connection. They use what? Fiber optics. Another application of light wave is in medical imagery. So light waves are used in medical imagery techniques such as optical coherence tomography and photoacoustic imagery. So we also use what? Your light wave in the medical field. It is also used in spectroscopy. So light wave are used to study the particle properties of materials and analyze their composition. So they use our light wave also to determine the composition of materials and their properties. So that takes us to reflection of light, which is one of the behavior of light wave. Reflection of light. And we explained earlier that when light is incidented on a surface, that it bounces back from that surface, thereby changing its direction. This principle is called reflection. And we have two types of reflection. We have what is called the regular reflection, and we have the irregular or diffuse reflection. So when light hits a smooth surface, so if I have, let's say this is a plane mirror, this is a smooth surface, and I have my normal ray here, and I have an incident ray coming this way. Let's say incident ray coming this way. I have incident rays coming this way. These rays will be reflected this way. So this is what we call regular reflection. Why? This surface is smooth. So whenever rays of light hit a smooth surface, they are reflected at the same angle from the surface. So, but when we have diffuse reflection, when we have rough surfaces, let's say this is a surface and then a beam of light is incidented on it. Now, because they'll be hitting this particular surface at different angles, they will scatter. So we're having a scattered form of reflection. And this type of reflection is what we call diffused reflection. So this is diffused reflection. And this is regular reflection. So that takes us to the laws of reflection. The laws of reflection. The first law of reflection states that the angle of incidence is equal to the angle of reflection. The angle of incidence is equal to the angle of reflection. What does this mean? If I have a plane surface this way and I have my normal ray and light is incidented on it at a particular angle, this angle here is called the angle of incidence. The angle of incidence. So this light is coming from a source, so we'll call it what? The incident ray. This light here is called incident ray. And this angle here is called the incident angle. And when it hits this surface, it is reflected from this position. So it's moving out from the source. So it's moving out from this surface. Here it is coming to the surface. Here it is moving out from the surface. So this is the reflected ray. Reflected ray. So the angle here is equal to this angle. That's the first law of reflection, that the angle of incidence is equal to the angle of reflection. So if this angle here is 30, automatically the angle here will also be 30 according to the law of reflection. So the second law of reflection says that the incident ray, the reflected ray, and the normal ray all lie on the same plane. What does this mean? If I have a plane surface, what it is saying is that if I have it, let's say this is a plane mirror, I have a plane mirror. What it is saying is that the incident ray which is coming to hit the mirror, this is the incident ray coming to hit the mirror, the reflected ray that is moving out from the mirror, and the normal ray that the mirror has, which is perpendicular to the mirror, they are all lying on the same plane of the mirror. That is what second law of reflection. So the incident ray, the reflected ray, and the normal ray all lie on the same plane. That is the second law of reflection. So that takes us to the applications of reflection. How do we apply reflection? We apply the principles of reflection in mirrors. So mirrors are used in our everyday life for personal grooming, for decoration, and optical instrument. So these mirrors are using the principle of reflection. That's why you can stand in front of the mirror and see yourself reflected back to you. We also have these applications of reflection in optical instruments like your telescope, your microscope, your binoculars, etc. that we use for magnifying objects and items. So when you put your blood samples in your microscope and you observe it under the microscope, what you are doing is what? Applying the principle of reflection. It is also applied in laser technology. Lasers are used for cutting materials and for welding materials. So the principle of reflection is also applied in this technology. Okay, so that's that, and we go to the examples of reflection. The first example of reflection is mirror reflection. When you see yourself in a mirror, is an example of mirror reflection. So we also have what is called water reflection. If a water body, a standing water body, that's a water body that is not moving. When you stand very close to it, discover that what you see an image of yourself and the image of the surrounding. If there are objects around that particular water body, they can be viewed from the water body. They also have retroreflection. This is seeing a reflection of light back to its source, such as with reflective clothing. If you have some of these cloth that when light hits it, it shines back at you. Or you can also see an example of such reflective surfaces, like when you point light directly at your television or your screens generally, it is reflected back to you. That is what we call retro reflection. So we have come to the end of this class. If you have any question, drop it in the comment section. Don't forget to subscribe and turn on the notification bell just when we drop, so that when we drop the next video, you will be notified. Thank you.